Hello students, very good morning students. This is Dr. Eustace Russell, Assistant Professor of Mechatronics Engineering at Sri Muthukumaran Institute of Technology. So far we are seeing the subject called Robot Dynamics and Control. Today we are going to discuss the Unit 5 for your reference. Upcoming slide we will see the syllabus and the content. Unit 5 is force control. It's having constraint dynamics, static force, torque relationship, constraint surfaces, natural and artificial constraints, network models, and impedance, impedance operators, classification of impedance operators, force control trajectories, then impedance control, hybrid impedance control. In that, we are going to see some important topics: introduction to constraint dynamics, degrees of freedom and constraints, static force and torque relationship, constraint surface, natural constraints, artificial constraints. Before going on to that, we must know what is constraint dynamics. Constraint dynamics deals with the motion of robotic manipulators when their movement is resisted by the environment, task, requirements, or mechanical limitations. Example, robot polishing a surface, plug-in hole assembly, welding along a predefined path, robotic surgery, free motion versus constrained motion. Robot moves without contact, that is free motion. Everybody knows that, without any restrictions. All DOF available, that is all degrees of freedom will be available. Then constrained motion, robot interacts with the environment. Some DOF restricted, that is only some of the few degrees of freedom only allowed. Industrial example means when a robot polishes a flat metal plate, it must maintain continuous contact with the surface along a specified path. Degrees of freedom. As we already know, everybody knows that a number of independent motions available to the robot. That is a motion that is available. Cartesian DOF, a rigid body in a space has 6 degrees of freedom. Translational, rotational. Translational means it is X, Y, Z. Rotational, roll, pitch, yaw. Degrees of freedom equal to 6 will be taken into account. Degrees of freedom equal to 6. Then example, industrial robot, 6 revolute joints and 6 DOF. The higher the DOF, the greater the flexibility of motion. Then what are constraints? Constraint definition. A constraint resists 1 or more degrees of freedom of a robotic system. Sources of constraint. It is environmental, that is walls, floors, and work surfaces. Mechanical, in terms of mechanical, we have a joint limits and link resistance, task based following a path, maintaining contact force. Example, a robot moving on a table cannot move downward through a table surface. For example, if it is moving on a table, it cannot moving downward through the table surface. That is one of the constraints here we can see. Mathematical representation of the constraints. Constraints are represented using equations. We can see general constraint equation is given by pi of q equal to 0, where q equal to joint variables and pi of q equal to constraint function. Example, motion resistance that is restricted to the plane z equal to 0. Robot can move along in xy directions. Interpretation, we can see constraint equation define the allowable region in that where it is moving. Equality and inequality constraints. Exact restrictions, that is nothing but pi of q equal to 0. Example, robot end effector remains on a plane, that is z equal to 0. There is no height that will be maintained here, it will be under 0 only. Then inequality constraints, boundary restrictions, that is pi of q equal to that is less than or equal to 0. Then joint limits we are having minus 90 degree, less than or equal to theta, less than or equal to 90. Obstacle avoidance, distance greater than d minimum. Application safety systems, motion planning. Then constraint forces, when the motion is resisted, reaction forces appear. Example, wall contact, robot pushes wall, wall generates reaction force. So in that Newton's third law, F of F robot equal to F wall. So in this we have the some obstacle will be there. Reaction force will occur in that. Then based on the Newton's, we know that aware of the Newton third law. There is one opposing force will be there. Importance: constraint forces affect stability, accuracy, actuator, torque. Then application: grinding, deburring, surface finishing. Then static force torque relationship. Static force torque relationship defined how linear forces and rotational movements interact without acceleration. It is governed by the principle of static equilibrium, which mandates for any stationary object the sum of all forces is 0 and sum of all torque about any pivot point is 0. Mechanical properties that govern this relationship include, that is, first of all, torque calculation. Torque tau is the rotational equivalent of force. It is a product of force and the perpendicular distance from the pivot point to the line of action of the force, also called lever arm. Tau is given by F into R into sine theta, where theta is the angle between the force vector and the lever arm. Then equilibrium condition, as we discussed in engineering mechanics, we already studied in engineering mechanics. These are the equilibrium conditions for a system to be in static equilibrium. Two fundamental conditions, that is translation and equilibrium. Summation of F equal to 0, all force cancel each other out. Rotational equilibrium, summation of the tau equal to 0, all clockwise and counterclockwise torque are perfectly balanced. Robotic and mechanical application. In mechanisms like robotic arms or articulated joints, forces at the end effector are related to joint actuators using a manipulated Jacobian matrix J. Static force is related to the required joint torque by the equation tau equal to Jt into F. Jt is the transpose of the Jacobian matrix. Then Jacobian transpose and force torque relationship. Jacobian transpose. This Jacobian already we discussed in unit 1 also in Jacobian matrix. Here also we are seeing the Jacobian transpose. Jacobian transpose establishes the relationship between the force applied at the torque end effector and the torque required at the joints. That is force torque relationship tau equal to, that is transverse Jacobian. F is nothing but end effector force vector. Physical meaning: Jacobian map joint velocity to end effector velocity. X dot equal to J of Q dot. Jacobian transpose performs the reverse operation by mapping forces at the end effector into equivalent joint torque. Principle of virtual work relationship is derived from the conservation of power. Transverse torque Q dot equal to transverse force X dot. Substituting X dot equal to J Q dot, tau equal to transverse Jacobian into F. If a robot applies a force to the wall, Jacobian transfer determines the torque each motor must generate to produce that force. Application: force control, impedance control, assembly operation. Then surface finishing, robotic grasping. Then constraint surfaces. Constraint surface is a geometrical boundary that resists robot motion based on the natural constraints, constraint imposed naturally by the environment. Example: robot touching a wall, surface contact, wheel rolling without any slipping, gripper grasping an object. So these are for sphere and cylinder. The equation it is mentioned. Sphere, everybody knows x square plus y square plus z square equal to r square. Cylinder x square plus y square equal to r square. Plane, for a plane z equal to 0. Artificial constraints deliberately imposed by software or controller based on the software. Example, virtual fixtures, robot allowed to move only along a path. Surgical robots prevent movement into sensitive regions. Industrial robot virtual safety zones. Benefits: improved safety and better have a better accuracy and precision also will be attained. These are the various references which I used to prepare this content. Kindly go through it. Thank you, students, for your kind attention. Kindly subscribe the video, share this video to your friends. We will meet in the upcoming lecture videos of this unit 5. Thank you, students.